In this section, we're looking at semiconductors. Specifically, we're looking at acceptor and donor atoms. But just some material before that, we have this outline, and these notes can be found in the description linked below the like button. We have information on intrinsic semiconductors. Semiconductors are materials whose resistance can be varied over a wide range by adding controlled amounts of impurity atoms. This is called doping. So whenever we add things here, we're doping our semiconductors. Intrinsic semiconductors are pure without doping. Next, we're going to look at non-intrinsic semiconductors, so just semiconductors, and that has to deal with our doping here. And this is done at room temperature 300 K. And it has enough thermal energy to break some bonds and create electron-hole pairs. Now, these free electrons that break away, so we see we have a plus here and a minus here. The minus is for electrons and the plus is for holes. That's just something you have to remember. You can think of the positive with our smaller word, which is hole, and the negative, it's longer. It's not really longer than the plus, but it is horizontal based, and electron is a longer word. So that's how I like to think about it. Or you can think of it like this. So these free electrons and holes are charge carriers, and they can move around and conduct electricity. P is the number of free holes, and this is represented with a positive. N is the number of free electrons, and that is with a negative. So electrons are negative and holes are positive, right? Well, P is positive. That has to go with holes, and N is negative. That has to go with electrons. So it's kind of like a double way to remember it if you forget the other way. Now we're going to look at doping, and we are going to look at our acceptors. So doped semiconductors. Semiconductors can be doped with different materials to add more electrons or more holes. So donor atoms specifically have 5 electrons in the outermost shell, so they can be used to donate an extra electron. So if we look at the middle here, we see that we have a +5 where everything else is +4. With our +4s, we have 4 negatives around it, right? Well, with this +5, it's going to give us an extra negative. And that's our n-type, right? So whenever we add an electron in here, this donor atom has 5 electrons, but we only have 4 spots, right? So what do we do with it? Well, it's going to go into this space right here. Free electron donated by our impurity atom, which is the value that we have here, the +5. So since the extra electron is not part of a covalent bond, very little energy is needed to free it so it can conduct current. So it's just going to be sitting there, and it can move around as freely as it likes. It'll have less resistance than if we try to pull one of the negatives away from our bonded or covalent bonded atoms. So, and these are our valence electrons when they're inside of a bond. The result of adding donor atoms is n-type silicon. And n-type, again, is, you can think of it as having more negatives, and negatives are electrons. And then we have information about what actual atoms can be used as donors. Now let's look at acceptors. So acceptors have 3 electrons. You can think of a donor, right? A donor is going to have more. That way he can give away more. And an acceptor needs to have less, so it can take more in. And a donor, you're losing, right? You're giving away, so that's where the negative comes from. Acceptor, you're gaining. So that's where the positive would come from. Now, acceptor atoms have 3 electrons, right? So if they only have 3 electrons, well, only these 3 parts are going to have covalent bonds. And we're going to have a hole here. So let's look on how we could fix that. So in the outermost shell, they can be added to accept an electron, which creates a hole. Acceptor atom created a hole, and an adjacent atom's electron filled that hole. That's how we would solve this. So our electron from over here accepted this atom, and it creates a hole. So the electron over here with this bottom +4 would go with our +3, and then a hole is created here. Now, when our holes and electrons leave, so when they leave immobile ions. And so once this happens, the atoms can't move again, and they are stuck with a plus or minus charge. And that is it for acceptors and donors, the difference between them. Acceptors have 3 electrons, And donors have 5 electrons because they need to donate one, while acceptors need to have room to accept. And a p-type is going to be a negative because P is for holes. In holes, you can think of it as positive. P for positive. And N is for our negative, the electrons. It's a longer word. And that is represented with negative N-type. So we have positive P-type and negative N-type. So those are the very specific things to remember. Remember, the P is equal to the number of free holes, and P is positive. N is equal to the number of free electrons, that's negative. And then remember with our donors that have 5 and our acceptors that have 3.